For decades, data engineering has been limited by a specific physical link. In a traditional database, the hard drives that store your data and the processors that run your queries are wired together inside the same machine. This coupled system has a critical flaw. Scaling up requires buying an entirely new server, meaning you have to pay for expensive new CPUs even if you only actually need more disk space. As datasets grew into the petabyte range, this model hit a hard physical ceiling. A single machine, no matter how powerful, eventually runs out of the local resources required to process modern analytical workloads. BigQuery addresses this ceiling by restructuring the database itself, replacing the single machine model with a distributed system. This is what is meant by serverless architecture. While servers are still physically present, Google completely abstracts the management, scaling, and provisioning of those servers away from the user. This video explores the mechanics of that abstraction, a system that separates how data is stored from how it is processed, to allow for queries across petabytes of data in seconds. To understand the efficiency of this model, we have to look at the architecture from the ground up, starting where the data actually sits. This is the storage layer, a distributed file system organized into optimized columnar sectors. The storage grid scales capacity automatically as you upload data. Above this sits the compute layer, a massive cluster of processing nodes completely separate from storage. This separation creates a challenge. How can processors analyze data without massive network delays? Google solves this with a proprietary petabyte network. This internal fabric moves data so fast that physical distance doesn't impact performance. This network allows both layers to expand horizontally. You can add more disks or processors without one ever becoming a bottleneck. This specific physical mechanism, two distant layers linked by a high-speed network, is the foundation that makes serverless scalability possible. The advantage of this separation becomes clear the moment a user submits a SQL request. A monolithic system processes queries linearly, creating a slow queue that is limited by the power of its local processors. BigQuery takes a different approach. A central node intercepts the query and fractures it into thousands of parallel subtasks. The platform allocates idle CPUs to simultaneously process these fragments. During reaggregation, these nodes send results back up the execution tree, compiling one final result. This architecture allows the system to complete full table scans across terabytes of data in a few seconds. Because the system is serverless, it only provisions and bills for these thousands of processors during the exact seconds the query is running. This speed is the result of applying thousands of decoupled processors to a single problem in parallel. Traditionally, data engineering has relied on the ETL pipeline: extract, transform, and load. Historically, data had to be physically copied and moved into the central warehouse's native storage before it could be analyzed. BigQuery bypasses this ingestion step using a mechanism called Federated queries. Because the compute engine is separate from native storage, it's agnostic to where data lives. It targets external sources, like cloud storage buckets or Cloud SQL databases. BigQuery points its compute network at these external systems, processing data in place without a duplicate copy. While this approach has slightly higher latency than native storage, it significantly reduces the time to insight by removing the need for data migration. Federated queries transform the platform into a universal compute engine, capable of analyzing data across the entire cloud environment. These internal mechanics shape how engineers interact with the system in real-world production environments. While the web interface is used for ad hoc analysis, the system's primary utility is realized through programmatic integration. Engineers use client libraries and REST APIs to connect BigQuery directly to external applications, Python scripts, and automated machine learning pipelines. This model allows a petabyte-scale warehouse to function exactly like a lightweight microservice. An application sends a request, and the system returns the data. This removes the need for the complex connection pooling and infrastructure management typically required to link applications to legacy databases. This simplicity highlights BigQuery's primary value, the abstraction of technical complexity. By masking the hardware layer, the system eliminates the need for manual database administration, disk defragmentation, and cluster sizing. From the bottleneck of the monolithic server to a fully parallelized and federated system, the architecture has been rebuilt for scale. This serverless fabric changes the role of the data engineer. When the infrastructure manages itself, engineers can focus entirely on deriving insight from their data.